For a long time, the solar system seemed like a solved puzzle. We knew the planets, their orbits, and even many objects beyond Neptune. But in the farthest regions, where sunlight is weak and ice dominates, some small bodies began to behave strangely. They were not randomly distributed. Their orbits seemed aligned, as if an invisible force was organizing everything. This is exactly the kind of clue that gravity leaves when something large is hidden. The hypothesis of Planet 9 arises from this: a distant world, large enough to shape trajectories, but too dark to be easily seen. If it exists, it is not just another planet. It is a giant missing piece in the story of our own cosmic backyard. What makes this story fascinating is that it doesn't start with a spectacular photo, but rather with mathematics and patience. Astronomers analyze the orbits of trans-Neptunian objects, small, icy worlds far beyond Neptune, for decades. When you measure positions, inclinations, and distances, you expect a certain natural scatter. However, in some datasets, a pattern emerged. Several of these objects had perihelia and orbital orientations that seemed to point to the same region of space. This could happen by chance, but the probability starts to become uncomfortably low when the alignment persists across different analyses. The simplest explanation, in gravitational terms, would be a distant, massive body, pulling and shepherding these orbits over millions of years. Planet 9 would be that invisible hand, rearranging the apparent chaos. To understand the hypothesis, it is necessary to feel the size of the solar system. Neptune is far away, but it is still relatively close compared to what comes after. Beyond it, there is the Kuiper Belt, a region full of icy bodies. Even farther out, there are areas where the presence of the sun is almost symbolic. If Planet 9 is out there, it could have an enormous orbit, taking thousands of years to make a complete revolution. This means it would spend most of its time even farther away than we imagine. And the farther away it is, the less light it receives, and the less light it reflects. It's not like searching for a lighthouse. It's like searching for a grain of coal in a dark stadium. That's why the search depends on predictions. Where to look, when to look, what kind of brightness to expect. It's science guided by gravity, not by ready-made images. The hypothesis of Planet 9 gained traction when computational models showed that a planet with a few Earth masses in an inclined and elongated orbit could explain several strange behaviors at once. Not only the alignment of certain objects, but also the existence of highly inclined orbits, almost sideways in relation to the solar system's plane. The gravity of a distant body acts like a slow choreography. It doesn't give a single push. It repeats small disturbances over eras. The result can be an entire family of objects that seem to obey the same command. But there's a problem. You can explain data with different models if you have enough variables. So the question becomes, is it a real planet, or are we seeing a pattern produced by observational bias? This is where the story stops being a legend and turns into a serious scientific dispute. The observation bias is a silent enemy. Telescopes do not observe the entire sky with the same depth. Some regions are studied more, at certain times of the year, with specific instruments. If you discover objects mainly where you search the most, you may end up finding alignments that reflect your own search map. For this reason, part of the scientific community questions whether the pattern that motivated Planet 9 is robust enough. Still, even with criticism, the hypothesis has remained alive because new simulations and new objects found have continued to fuel the debate. It's like an ongoing trial. Each discovery is a witness for or against. And as long as there is no direct image, the evidence will be indirect, gravitational, statistical. This does not mean weak. It simply means that we are trying to see a world using the effect it causes, like deducing a ship by the wave it leaves in the sea. Gravity is the main language of this search. When a massive planet exists, it alters the dynamic structure of everything around it. Small objects become sensitive to this field and can have their orbits tilted, elongated, or even inverted over enormous timescales. Planet 9, if it has something like 5 to 10 Earth masses, would be large enough to influence a set of trans-Neptunian bodies, but distant enough to avoid being easily detected by brightness. This creates a curious signature, a strong effect on very distant objects without an obvious body in the telescope. Moreover, some models suggest that this planet could explain why certain objects seem to be detached from Neptune's direct influence. It's as if there is a second conductor, playing a slow rhythm at the periphery of the solar system. If Planet 9 is real, what would it be like? We're not talking about a gas giant like Jupiter. The most common hypothesis suggests a super-Earth or mini-Neptune-type planet. Larger than Earth, perhaps with a rocky core and a thick layer of gases or ice. At such low temperatures, the atmosphere, if it exists, could be very different from what we imagine, with compounds freezing and sublimating slowly. The sunlight would be weak, and the sky a deep black. But don't confuse cold with inactivity. Even distant worlds can have internal heat, radioactivity, and perhaps layers where ice behaves like rock, flowing on geological timescales. Still, it is unlikely to be habitable in the popular sense. The value of Planet 9 lies not in being a new home, but in revealing how the solar system formed. The origin of Planet 9 is a mystery as great as its location. One possibility is that it formed near the giant planets and was then thrown far away during the turbulent infancy of the solar system. In the first millions of years, the planets migrated, exchanged energy, and reorganized orbits. In this scenario, an intermediate planet could have been ejected into an extreme orbit, but still bound to the Sun. Another hypothesis is even bolder. It could have been captured from another star during a close encounter in the star cluster where the Sun was born. This sounds rare, but in dense environments, gravitational encounters happen. If Planet 9 is a captured outsider, it would carry a historical signature from the Sun's nursery. In both cases, finding this planet would be like discovering a fossil. Thinking about gravitational capture changes the scale of history. It is not just the solar system in isolation, but the solar system is part of a community of stars that were born together. If the Sun emerged in a cluster, it had close neighbors in the beginning. A stellar passage a few hundred astronomical units away could alter orbits and even steal planets. This is hard to prove, but not impossible. What science does is look at consequences. The distribution of distant objects, inclinations, disturbances consistent with an ancient event. Planet 9 could be a survivor from that era, an object that stayed too far away to be integrated into the set of known planets, but close enough to still disturb smaller bodies. If this is true, discovering Planet 9 would be like recovering a lost memory. How to search for a planet that may take millennia to orbit and receives almost no light. The strategy is to combine orbital predictions with large sky surveys. Wide-field telescopes, capable of photographing enormous areas repeatedly, are essential. Astronomers look for a point of light that moves slowly against the background stars. The problem is that, at that distance, the movement can be so subtle that it blends with noise, and the brightness can be so faint that it disappears in common exposures. Therefore, the search requires repetition, image comparison, and algorithms to identify tiny movements. Additionally, Planet 9 may be in a region of the sky with a lot of Milky Way star pollution, making separation difficult. It is a hunt of extreme patience. There is also an important difference between not seeing and not existing. The sky is vast, and our searches have limits of sensitivity. Many previous surveys did not have the range to detect such a distant and dark object. This means that Planet 9 may have gone unnoticed, not because it is hidden on purpose, but because it is beyond technological reach or outside the most observed regions. Modern science is always expanding this window. Better sensors, faster processing, and larger catalogs increase the chance of finding something like this. Still, there is a point where uncertainties accumulate. If you do not know the exact orbit, you can aim at enormous regions, and each region requires time and good conditions. Each new trans-Neptunian body is another piece of data that narrows the map. A little discussed aspect is that Planet 9, if it exists, may also influence the Oort cloud, that hypothetical region even farther out, a reservoir of long-period comets. By slowly altering orbits, a massive planet can deflect trajectories and send some bodies inward toward the solar system over ages. This does not mean an immediate shower of comets, but a change in statistics over time. Gravitational dynamics are like a tide, almost imperceptible in the moment, powerful in the accumulation. This possibility makes Planet 9 relevant not only for explaining alignments, but for connecting various layers of the solar system. The Kuiper Belt, scattered objects, inclined orbits, and potentially the farthest boundary. But elegance is not enough. It needs confirmation. And this is where the scientific tension arises. How much indirect evidence is enough before calling something real? In the history of astronomy, we have predicted planets before seeing them. Neptune was confirmed after anomalies in Uranus's orbit. But there were also false alarms, like Vulcan, a hypothetical planet to explain Mercury's orbit, which was ultimately explained by general relativity. Planet 9 lives exactly in that territory, between well-founded prediction and the possibility of an alternative explanation. This makes the search even more important because the answer, whatever it may be, teaches us something. If we find the planet, we rewrite the inventory of the solar system. If we don't find it, we may discover that our data was biased or that there is another dynamic physics at play. In both cases, the outcome is progress. Let's talk about what the models usually predict. Many scenarios place Planet 9 in a very elongated orbit, with perihelion and aphelion extremely distant, and an inclination relative to the plane where most planets orbit. This means that, from our point of view, it may be in regions of the sky that we do not intuitively associate with the plane of the solar system. Furthermore, it may currently be in the farthest part of its orbit, where it is darker and slower. This makes the search more difficult, but also more specific. If you combine the alignment of the observed objects with simulations, you get probable ranges in the sky. With each new object, these ranges can change. It's like recalibrating a triangulation. Planet 9 is not just anywhere. It is in a set of locations compatible with the data. There is also the issue of intrinsic brightness. A distant planet may be cold, but still emit weak infrared radiation, especially if it has internal heat. Therefore, it's not just the visible that matters. Infrared observations can be decisive because they capture heat, not just reflected light. However, this requires specific instruments and catalogs, in addition to separating a weak signal from a background full of sources. Some searches have already used infrared data to rule out certain regions or certain types of planets, but possibilities still remain. Planet 9 may be smaller, darker, or have a composition that makes it difficult to detect. It is a target that eludes due to details. And at the same time, it is a target that should exist if gravity is truly leaving that signature. This duality keeps the story alive. The scientific community is not unanimous, and that is healthy. Some researchers argue that the number of objects used to infer the alignment is still small. Others point out that as new objects are discovered, the pattern may weaken or change shape. There is also the hypothesis that Neptune, along with resonance effects and observational selection, could produce some of the behavior without an extra planet. There are even more exotic ideas, such as the possibility of a small primordial black hole exerting influence. This appears in discussions as a theoretical exercise, but it serves to illustrate a point. A gravitational signature does not automatically point to a common planet. It points to mass, and mass can take different forms. Therefore, the search for Planet 9 is also a search for rigor. When we talk about trans-Neptunian objects, we are not talking about one or two cases. It is an entire population of small worlds, each with its own orbital history. Some are prominent, with orbits that seem isolated from the direct perturbations of Neptune. Others are scattered, with trajectories that suggest ancient encounters. And there are also objects with extreme inclinations, almost perpendicular to the main plane. Planet 9, in some models, acts as an organizer of this diversity, creating dynamic families. But it is also possible that this diversity is the product of multiple events: planetary migration, stellar encounters, and resonances. Finding Planet 9 would be like finding the missing binding that explains why the pages are the way they are. There is an emotional reason behind popular interest. The idea of a new planet evokes classic discoveries, as if we are living in a new era of exploration. But scientifically, the importance is even greater. If a planet with several Earth masses is hidden so far away, it changes models of planetary formation. Why did it remain? Why didn't it become a giant like Uranus and Neptune? These questions connect our solar system to planetary systems around other stars. Today we know that super-Earths and mini-Neptunes are common in the galaxy. Perhaps Planet 9 is a local example of a frequent category, just under extreme conditions. Or maybe it is a rare dynamic accident. In both cases, it serves as a bridge. What if Planet 9 doesn't exist? This possibility needs to be considered honestly. Science does not commit to a hypothesis out of desire, but out of evidence. If new discoveries show that the alignment was an artifact of selection, or if deep surveys cover the likely regions without detecting anything compatible, then the hypothesis will have to be revised. This would not be a failure. It would be learning about how the outer solar system really works, and about how our methods can be misleading. Often, a strong hypothesis acts as a driver. It compels better data collection, the construction of telescopes, and the creation of more rigorous analysis techniques. Even if Planet 9 is discarded, the outcome could be the discovery of dozens of new small worlds. Sometimes, you search for a giant and find an entire continent. For now, Planet 9 remains a mathematical shadow. It is a hypothesis based on patterns, simulations, and intense debates. This places you, now, in the midst of a real-time investigation. It is not a closed story. It is an open quest, with new discoveries possible any year. And the main question remains simple and powerful. Is there, in the dark fringes of the solar system, a large world yet unseen? If the answer is yes, confirmation will be a historic moment. If the answer is no, then we will have to explain why the outer solar system is producing these signatures without an additional planet. One way or another, what is at stake is our understanding of the edges of home. And it is precisely at the edges that science often finds its best surprises. One of the most promising routes to finding Planet 9 is to look for not just reflected light, but heat. Even a distant planet can retain internal energy for long periods, and this can appear as a very faint glow in the infrared. The challenge is that the infrared sky is also filled with sources: stars, dust, galaxies, and instrumental noise. So the search requires filters, comparisons between epochs, and models that predict the expected brightness for different masses and compositions. If Planet 9 is a mini-Neptune, for example, it may emit a bit more in the infrared than a rocky super-Earth. But if it is dark, compact, and very cold, it may escape detection nonetheless. This uncertainty keeps the scientific suspense alive. Each type of planet requires a different strategy, and this turns the search into a game of testable hypotheses, where you gradually eliminate scenarios, narrowing down the target. Modern sky surveys function like gigantic censuses. They photograph the same region repeatedly, cataloging billions of sources and looking for changes. For a distant planet, change is a tiny shift, almost too slow to be perceived without precise comparison. That's why algorithms become as important as telescopes. The idea is simple. If you have images from weeks, months, and years, any object in the solar system moves, even if just a little. Planet 9 would have an extremely subtle movement, but still detectable with enough data and good calibration. The problem is that false positives appear all the time. Noise, artifacts, atmospheric variations, closer objects that move faster. So the search requires layers of confirmation. Finding Planet 9 will be less like discovering a shooting star and more like validating a hidden signature in an ocean of data. There is a crucial point. The hypothesis of Planet 9 makes predictions, and predictions can fail. If you point to high-probability regions and they are thoroughly searched without any candidates, that forces a model adjustment. Perhaps the mass is smaller, perhaps the orbit is different, perhaps the planet is further away, or perhaps the phenomenon has another cause. This ability to be refuted is what makes the hypothesis scientific. Many fans want a definitive answer now, but science works in stages, like an investigation that eliminates suspects. Each round of observations reduces the realm of the possible, and this reduction is already valuable. By mapping the outer solar system with greater precision, we discover new objects, new orbital classes, and new questions. Even if Planet 9 remains invisible for longer, the search is building a real atlas of the boundaries of the solar system. And it is this atlas that, in the end, may reveal the right path. With each new, distant object, the story changes a little. It's as if we are completing a map with previously unknown islands. Some of these bodies are so distant and peculiar that they defy simple explanations. They seem disconnected from Neptune, as if something has pushed them into a rare orbital state. Planet 9, again, appears as a unifying explanation. But there are also alternative scenarios, such as past interactions between Neptune and a more massive disk of small bodies, or even ancient stellar encounters. Therefore, the focus is not just on counting objects. It is to precisely measure their orbits and understand the statistical distribution. How many have extreme inclinations? How many have high perihelion? How many truly align when you correct for observational bias? This work is slow, but it is the kind of slowness that builds certainties. In astronomy, patience is almost an instrument. Orbital resonances are another key element. They occur when orbital periods relate to each other by simple ratios, creating gravitational repetitions. Neptune already creates resonances in the Kuiper belt, trapping some objects in stable patterns. A Planet 9 could create even more distant resonances, shaping orbits in ways that today seem exotic. This would be a powerful indirect signature, because resonances leave traces in the distribution of semi-major axes and eccentricities. However, proving a resonance without seeing the planet is difficult, because the resonance depends on the position and mass of the perturber. Still, it is an active line of investigation. If you find groups of objects with consistent orbital relationships, this may point to a common agent. The beauty of this is that gravity does not lie, but we can misinterpret it if we have incomplete data. Therefore, each conclusion comes with clear uncertainties and proposals for new tests. Let's return to the possibility of stellar encounters. If in the past a star passed relatively close to the solar system, it could have pulled objects into unusual orbits, and at the same time, altered the overall distribution of the outer solar system. This could mimic some signals attributed to Planet 9. The difference lies in the pattern. A stellar encounter may leave a broader and more chaotic fingerprint, while a continuous planet tends to produce more persistent alignments and dynamic families. But reality may be a mix. Ancient stellar encounters may have set the stage, and a distant planet may have continued the work of orbital organization over time. When you accept this complexity, you realize that the search for Planet 9 is also a test for our models of solar system evolution. It forces us to consider the Sun as a member of a larger stellar environment, especially in the beginning. Understanding this even enhances how we interpret disks and planets in other systems. And here appears an alternative that usually draws attention. What if it is not a common planet? Some researchers have explored the idea of a compact object, such as a primordial black hole, exerting the necessary mass. The proposal is speculative, but useful because it tests the essence of the argument. What the data requires is mass in a specific place, not necessarily a classic planet. If an optical search fails repeatedly, but the gravitational signature persists, alternative hypotheses become more attractive. However, a black hole would have different interactions with the environment and possibly detectable signals in rare events, such as gravitational microlensing or interactions with surrounding matter. We are still far from asserting something like this, but the mere fact that this hypothesis exists shows how science deals with uncertainty. It opens up possibilities, but demands clear observational tests. In the end, Planet 9 needs to leave some direct signature, whether through light, heat, or additional measurable effects. There is a difference between a popular mystery and a scientific problem. The popular mystery wants a dramatic ending. The scientific problem wants a solid set of data. That is why large observational projects are so important. They reduce the discussion of guesswork and increase the discussion of probabilities and limits. When a survey says, "We did not find," that is not empty. It means that within a certain brightness and in a certain region of the sky, Planet 9 cannot be. This cuts the map. And the more you cut, the more concrete the search becomes. The public sometimes interprets the absence of evidence as evidence of total absence. But that is not the case. Absence only counts within the range of the instrument and the method. That is why each new generation of telescopes reopens doors. Planet 9 may be waiting for just that technological leap to come out of the shadows. Imagine the environment of this possible planet. The sunlight would be so weak that the day would seem like an eternal twilight. Any atmosphere would be compressed by extreme cold, and common substances in the inner solar system would behave differently. Yet a massive planet could still have layers, internal dynamics, and perhaps even slow geological activity. Some models suggest that beneath a frozen crust, there could be enough residual heat to maintain internal processes. This does not mean oceans like those of Enceladus or Europa, but it shows that distant is not synonymous with dead. Still, the main value of Planet 9 is dynamic. It would be an orbital architect, a body capable of explaining why certain distant objects are where they are. Finding this planet would confirm that the solar system still holds gigantic secrets, even after missions and telescopes that seem to have concluded the count. There is also a cultural impact. The definition of a planet has been a topic of debate, as in the case of Pluto. If Planet 9 is found, it will reopen discussions about classification, boundaries, and even how we teach the solar system. But unlike Pluto, Planet 9 would likely be much more massive. It would fit more easily into the traditional concept of a planet. The irony is that it would be so far away that it would hardly participate in the everyday landscape of the sky, unlike the planets visible to the naked eye. It would be a planet by influence, not by presence. And that is a powerful idea. Something can be real, important, and decisive, even if it remains invisible to our direct experience. Modern astronomy thrives on this. Many of the largest objects in the universe are first known by their effects, then by images. Planet 9 could be the next emblematic case. To increase the chances of detection, the ideal strategy combines multiple wavelengths and multiple methods. In the visible spectrum, one looks for the weak point reflecting light. In the infrared, one looks for heat. In orbital dynamics, one looks for statistical coherence with a perturbator. And in special cases, one looks for microlensing, when the gravity of an object passes in front of a star and amplifies its light for a moment. This is rare but not impossible. The central point is that science works with redundancy. When 2 or 3 independent lines point to the same result, confidence skyrockets. Until then, Planet 9 remains a strong but unconfirmed hypothesis. And this is not a reason for frustration, it is a reason for fascination. We are witnessing the scientific method in action: prediction, critique, data collection, model adjustment, and new search. This is how the invisible is found. Sometimes the best way to understand is to use a metaphor. Planet 9 would be like a huge ship sailing far away, invisible in the dark, but leaving waves that reach us. The trans-Neptunian objects would be buoys, swaying in a coordinated manner. You don't see the ship, but you see the pattern in the buoys. The question is to find out if these waves come from a real ship or from a set of currents and winds that you haven't modeled correctly yet. This is the difference between a simple explanation and a complex explanation. The hypothesis of Planet 9 is simple, elegant, and testable. The alternatives often require combinations of effects. This does not make the alternatives false, but it increases the rigor needed to accept them. Science prefers what explains more with less, as long as the data supports it. That's why Planet 9 remains at the center of the debate. It is an efficient candidate to explain multiple signals. As the search progresses, one thing becomes clear. The outer solar system is less tidy than we imagined. There is a dynamic frontier, a place where the sun's gravity competes with disturbances from the interstellar medium, galactic tides, and distant encounters. In this region, small initial differences can lead to enormous outcomes after billions of years. This makes any conclusion more delicate, but also more interesting. Planet 9, if it exists, would be one of the main actors on this stage. It could explain why certain orbits resist complete scattering, why some extreme inclinations persist, and why there are objects in regions that seem forbidden by simple models. But again, only a direct detection will close the question. And when that happens, it won't just be a point of light. It will be a revolution in our cosmic cartography. There is a silent technological component that decides the hunt: data processing. Modern surveys generate gigantic volumes of images. Detecting subtle movement requires calibrating each frame, removing distortions, aligning stars, compensating for the atmosphere, and comparing epochs. This is done by pipelines, automated systems, and still requires human validation. A candidate for Planet 9 would initially be just a suspicious point. Then comes the confirmation. It appears again where it should, moves the right way, has consistent brightness, and is not an artifact. This process can take months, and even when a candidate seems promising, it needs to be observed by other instruments, on other nights, to eliminate coincidences. The frustrating part is that many candidates die along the way. The amazing part is that the method works. This is how the rare is found: testing, discarding, and refining until what cannot be ignored remains. The Planet 9 also forces us to confront an uncomfortable reality. Our intuition fails on enormous scales. We think of the sun as the dominant center, but at extreme distances, it becomes just a bright star in an infinite sky. Gravity still rules, but the brightness nearly disappears. If a planet is hundreds of astronomical units away, its world is another category of isolation. This makes the hypothesis seem almost absurd, yet at the same time plausible, because the galaxy is full of objects we do not see directly. What matters is the method. The hypothesis arose from real data and makes testable predictions. It can be confirmed or discarded. This is the kind of question worth pursuing because it does not depend on belief. It depends on observation. And each year of data improves our ability to respond. If the confirmation arrives, the announcement will be historic. And it won't just be about one more planet. It will be because we will have found a large object using primarily indirect signals. This would validate dynamic models and show that there are still large bodies hidden in our system. But it would also raise new immediate questions. What is the exact mass? What is the orbit? What is the composition? And how did it get there? These questions would fuel decades of research. Perhaps future missions could be imagined, although the distance makes everything extremely challenging. Still, the mere existence of a Planet 9 would make the solar system seem larger, richer, and more complex. And for those who love science, this is the best kind of news. A discovery that doesn't close a chapter, but opens several new ones.
And what if the hypothesis falls?
In that case, science wins anyway. Because in trying to find Planet 9, we will have expanded our catalogs, discovered new small worlds, and better understood the role of Neptune, resonances, and observational bias. Perhaps we will discover that the distribution of distant objects is more random than it seemed. Or perhaps we will uncover a different, equally profound explanation, such as an ancient stellar event that reorganized the outer solar system. The point is that big questions push technology and refine thinking. Planet 9 serves as a big question, and big questions have always been the driving force of astronomy. When you look at the edge of the solar system, you are looking at the edge of what we know. And it is precisely there that discoveries arise that change books, classes, and our very perception of our place in the universe. Perhaps the most beautiful aspect of this search is the contrast between silence and impact. Planet 9, if it exists, makes no noise, does not shine in the sky like Venus, and does not appear in famous photos. It acts in silence, pulling distant objects over millions of years. And yet, its effect may be great enough to be detected by minds that observe patterns. This shows the power of science, to see the invisible through logic and measurement. It also shows humility. Even in our solar system, we may still be incomplete. When we think we have explored everything, a new candidate for mystery arises. The frontier is not a wall, it is an invitation. Planet 9 is that invitation in the form of a hypothesis. A missing piece that may be out there, waiting for the moment when our eyes and our data are good enough to find it. The coming years are likely to be decisive because sky surveys are becoming broader and deeper. This means that regions previously little studied will be mapped with a new quality. If Planet 9 is in a difficult area, close to the dense plain of the Milky Way, the improvement of source separation techniques and temporal comparison may finally reveal a convincing candidate. If it is in a cleaner area, detection may be even more straightforward. And if it is nowhere within the predicted boundaries, then the models will have to change. Whatever the outcome, we will gain a more accurate map of the outer solar system. And when you have a better map, you start to see patterns that were previously invisible. This is how science progresses, not through a single magical moment, but through a sequence of improvements that, when added together, turn the impossible into the probable. In the end, Planet 9 is a question about boundaries. How far does the solar system really extend? How many large bodies might be hidden in the darkness? And what does the architecture of distant orbits reveal to us about the infancy of the Sun and the planets? The hypothesis exists because gravity has left clues. Now it is up to us to follow these clues with telescopes, data, and rigor. If confirmation comes, we will add a new world to our map and better understand the dynamics of the edges. If confirmation does not come, we will learn why the edges behave as if something is there, and that, too, will be a discovery. One way or another, the story is already worthwhile, because it shows that the universe still has room for surprises, even in the place we call home. Planet 9 is the reminder that knowledge is not a destination. It is a continuous exploration.